All right, Michael. So here's boosting in pseudocode. Okay, let me read it out to you and then you can tell me if it makes sense. So we're given a training set. It's made up of a bunch of xi, yi pairs. You know, x is your input and y is your output. And for reasons that'll be clear in a moment, all of your labels are either -1 or +1, where -1 means not in a class and +1 means you're in a class. So this is a binary classification task. Does that make sense?
So far.
Okay. And then what you're going to do is you're going to loop at every time step, let's call it lowercase t, from the first time step 1 to some big time in the future. We'll just call it capital T and not worry about where it comes from right now. The first thing you're going to do is you're going to construct a distribution. And I'll tell you how in a minute, Michael, okay? So don't worry about it. And we'll just call that d sub t. So this is your distribution over your examples at some particular time d. Given that distribution, I want you to find a weak classifier. I want your weak learner to output some hypothesis. Let's call that h sub t, the hypothesis that gets produced at that time step. And that hypothesis should have some small error. Let's call that error epsilon sub t, because it's a small number, such that it does well on the training set given the particular distribution. So I'm just rewriting my notion of error from the other side of the screen. So at every time step, we want you to find a weak classifier. That is, we want you to call some weak learner that returns some hypothesis, let's call it h of t, that has a small error. Let's call that epsilon sub t, which is to say that the probability of it being wrong, that is disagreeing with the training label, is small with respect to the underlying distribution.
So just to be clear there, the epsilon could be as big as slightly less than a half. Right? It doesn't have to be teeny tiny. It might actually be almost a half, but it can't be bigger than a half.
That's right. And no matter what happens, or even equal to a half. But, you know, we can assume, although it doesn't matter for the algorithm, that the learner is going to return the best one that it can with some error. But regardless, it's going to have, it's going to satisfy the requirements of a weak learner. And all I've done is copy this notion of error over to here. Okay?
Awesome.
Okay, so you're going to do that, and you're going to do that for a whole bunch of time steps, constantly finding hypotheses at each time step, h sub t, with small error epsilon sub t, constantly making new distributions, and then eventually you're going to output some final hypothesis, which I haven't told you yet how you're going to get that final hypothesis. But that's the high-level bit. Look at your training data, construct distributions, find a weak classifier with low error. Keep doing that till you have a bunch of them, and then combine them somehow into some final hypothesis. And that's the high-level algorithm for boosting, okay?
Okay, but you've left out the two really important things, even apart from how do you find a weak classifier, which is where do we get this distribution and where do we get this final hypothesis?
Right. So let me do that for you right now.